Okay, welcome to video 4. This is looking in a series of tangent planes, looking at tangent planes, and this fourth video is looking at why we care, like what are some applications of the tangent plane. So we have a function, and that function's going to have the equation 2x squared plus y squared. It's paraboloid. It's an elliptic paraboloid, to be exact. And so the graph is a bowl shape, and the tangent plane at a certain point, zoomed out far enough, looks like that. Watch what happens though as we zoom in. And again, and again. So the point behind this is that the difference between the tangent plane and the function is very little the more and more you zoom in. As we zoom in towards our point, this is the point 113. If we look at the tangent plane, it looks very much like the actual surface of the function. The tangent plane and the elliptic paraboloid become virtually indistinguishable as we get closer and closer to that point. Mathematically, what it means as we get closer and closer to that point means locally the surface looks linear. And so what we do with the tangent plane is use it to approximate the actual function. We're going to find that plugging into a tangent plane equation would be a lot easier than plugging into the actual equation, especially without a calculator. And so long as you stay close to the point, you get a pretty accurate approximation. So here's how that works. So we have the equation z minus z naught equals the x partial times x minus x naught, and the y partial times y minus y naught. So let's let x naught be A, unfortunately, here, and y naught be B. And what we're looking here at is the equation of the tangent plane. It's just in the variables A and B in terms of x, in place of x naught, y naught. And so we can use this to approximate the function nearby points. If we stay close enough to our point A, B, we can use it to approximate the function. So we have the function is actually approximately equal to the linearization of this function. Okay, use the tangent plane to approximate the function. It's called a linear approximation of our function at our point, and better off just calling it the tangent plane approximation. Let's see it used in an example. Our function is the square root of 20 minus x squared minus 7y squared. The point AB that we're interested in is the point 2, 1. So what we're going to do is move a little bit away from that. In terms of x, we're going to go down by 0.05. In terms of y, we're going to go up by 0.08. So the question is then, well, how does that affect the function? Changing x by negative 0.05, changing y by a positive amount of 0.08, can we still get an idea of how the function is changing? Now, if we were to actually plug in 1.95 and 1.08, we would need a calculator to be able to get an approximation. Watch what we can do just with the power of our brain, no calculator, and using the tangent plane as the approximation. All right, so our function is that, and our point is that, and now we're going to find the equation of the tangent plane, find the linearization. And so when x is 2 and y is 1, we have the fact that we'll have 2 squared, which is 4, and 1 squared, which is 1. So we have 20 minus 4 minus 7. It's 20 minus 11. It is a 9, and the square root of 9 is a 3. So the z value is a 3. Now here's the issue. When we alter x and alter y, how much does that 3 get altered by? Okay, let's take a look at it. So to make the equation with the tangent plane, you need the partial derivatives. The partial derivative of any function that's underneath a square root starts off with 1 over 2 times that exact same square root. It's like taking half of the function to the negative half power, simplified version, 1 over 2 square roots of that function. Then a chain rule comes in, so wait, don't stop there, please. Multiply by the derivative of the inside function, and we're talking about with respect to x. So the x partial of the inside is negative 2x. The negative 2's can cancel, and we have essentially x on top of that square root. We know the square root is a 3, and it's actually a negative x. And so we have negative 2/3 is the x partial at that 0.21. How about the y partial? Looks exactly the same as far as the beginning part, but when you go inside and take the y partial of the inside, you get negative 14y. And you can cancel the 14 and the 2 to give you a 7. And so we have negative 7y for our numerator, but the y value is 1, same, square root of 9 in the denominator. So negative 7/3 is the y partial at our 0.21. And these serve as the coefficients on x and y in our tangent plane approximation, our tangent plane equation. And so what we do is we take the partial derivative with respect to x and multiply by x minus a, and the partial derivative with respect to y multiply by y minus b, and then we have the original z naught value, or c if you want to call it that. So what we're saying is that our function is approximately equal to this linear approximation. We'd like to be able to plug the 1.95 and the 1.08 into our function, but instead we're going to plug it into our tangent plane. And you'll be amazed at the accuracy we're going to get by doing that. And so an approximation to the function at 1.95 and 1.08 is to plug in 1.95 and 1.08 into the tangent plane approximation. Watch what happens. Inside the parentheses, you'll get the amount by which you're changing x and the amount by which you're changing y. We go down by 0.05 in x, we go up by 0.08 in y. We have decimals, we have fractions, and we don't have a calculator, so somehow you have to be able to deal with that. And so what we're going to do then is change these decimals into fractions. 0.05, it's 5 over 100. 0.08, that's 8 over 100. And so we reduce these guys. 0.05 would be negative 1 over 20, and 0.08 would be 2 over 25. And so what we have is that the function at 1.98 and 1.08 is approximately equal to the original 3, and then we have these amounts here that involve the partial derivatives and the change in the x. We have negative 2/3 times negative 1/20 and negative 7/3 times 2/25. We don't have a calculator, but still we can handle this. This 2 and this 20 combined to be a 10 in the denominator, so that's 1/30. And then as far as the other one, it's going to be negative 14 over 75. And so common denominator would be between 75 and 30. It's 150. And so the 3 is 450 over 150. For as far as the 30, it needs to be multiplied by 5 top and bottom, so 5 over 130. As far as the 75, it needs to be multiplied by 2 top and bottom, so negative 28 over 150 to give us the final result of 455 take away 28, or 427 over 150. All with the power of our brain. And watch how close this is to the calculator answer. On the next slide, we'll go to a computer system and plug 1.95 and 1.08 into the square root and find out that the difference between our answer, 427 over 150, and the actual calculator answer is 1/100th. So with the power of our brain, we were able to get the answer correct to 1 decimal point. As far as rounding goes, it'll be corrected 2 decimal point. And so we're only 1/100th off using the tangent plane. And the reason why we're so close to the actual answer is because we only changed x and y by a small amount. So this is our first application of the tangent plane, using it to approximate the function value. See what happens if you dial down x by a certain amount and dial up y by a certain amount, finding the result in z. Okay, now let's formalize that a little more. So we have this linear approximation formula, and the x minus a is the change in x. Okay, it's the increment of x. For us in the last problem, it was negative 0.05 or negative 1/20. The y minus b is the change in y, the increment of y. In the last problem, it was 8 over 100 or 2/25. And so we call that dx and dy, the differential of x and the differential of y. And the question then becomes, well, what does that mean about z? We have these independent variables, x and y, and we change them. And then we want to know, in them at least, as far as the independent variable goes, these are exactly the same. Delta x is equal to dx, and delta y is equal to dy for the independent variables. Then you plug them into the formula. The question is, what happens to the dependent variable, z? So delta x is dx and delta y is dy, but what about z? Is delta z actually equal to dz? That's the question. Well, delta z is the actual difference in the z values. So it's the f of xy minus the f of ab. And the question is, what about dz? And so we're going to find that out. Honestly, what's going to happen is we're going to look at this equation and alter it slightly, and we'll see the answer. So here's the equation that we have. And then here's what dz is. The differential dz is called the total differential, and it's equal to the product of the partial derivative with respect to x times dx, the partial derivative with respect to y, times dy. Looks very familiar from what's here. Is the partial derivative with respect to x times dx, the partial derivative with respect to y times dy. It's called the differential. You see, the function is approximately equal to the original value of the function plus the differential, the total differential. This here, together, these pieces make up what's called dz. Okay, so this tangent plane is now used to help us approximate a function. If we move that over to the other side, basically the delta z is approximately equal to dz. Okay, great. The key is that we got to keep the delta x and the delta y small. And so we'd much rather use dz than actually going to a computer and trying to use delta z. And so that's the power of the tangent plane, that you can approximate and not have to result to anything as far as computer-wise. Here's a question. We have a right triangle, and we know that two legs are measured with some measuring tool to be 5 and 12. It's a right triangle. These are the two legs, but maybe the tool was off. Maybe it's not calibrated correctly, and perhaps that it could have been off by 1/5 of a centimeter. Notice the units here. We're talking about meters, and then the amount that it could have been off, the possible error, is in centimeters. Okay, and so let's call the left and right dimension x, the up and down dimension y, and what we're saying is that the area of the triangle, the first part is asking about the area. The area of the triangle is the 1/2 the base times the height. In the right triangle, it's 1/2 the product of the legs. And so we have 1/2 of 5 times 12 would be what the area is, 30. Now, but this could have some differential change, like it could be off by 1/5 of a centimeter. And so we have to figure out then, how would that change your area? So we take an x partial, we get half of y. We take a y partial, we get half of x. And we go into the formula. We gotta be careful about units though. We either choose to do the whole problem in meters, or we do the whole problem in centimeters. It's very different. Okay. And so we're gonna decide to do the whole problem in meters. So this 0.2 centimeters, this 1/5 of a centimeter, that's just gonna be 1/500 of a meter. Okay, that's the delta x. It was also the delta y. 0.002 of a meter, 2/1000th of a meter. 1/2/1000th of a meter. So 1/500th of a meter. And so if we change x by 1/500th of a meter, we change y by 1/500th of a meter, the question is, what happens to the area? So the formula is that the change in area is based off of the product of the partial derivative and the change in each of the variables. And so we take half of y, we multiply it by 0.002. We take half of x and we multiply it by 0.002. So with x being equal to 12 and y being equal to 5, and once again, decimals and fractions mixed in together, let's go either all decimals or all fractions. So here we're going all decimals. See if we can handle that. This 2 and this 0.002 makes this guy 0.001. That is 1 over 1,000, and you multiply that by 5, you get 0.005. This 2 and this 2, change that to a 1, and we have 0.012. Add these two guys together, and it says that your area is going to be off by 0.017 square meters. The question becomes, is that acceptable? Is this tool going to be something that you could rely on? Is it reliable? What's your tolerance? What are you allowed to have as your error? So this is the maximum error. It's up or down, positive or negative. So we're just using the absolute value there. And so the maximum error in the calculated value is going to be 0.017 square meters. What's better, though, is to understand what percent is that of the actual value. I mean, if the value is 30 square meters and you are 0.017 off, your error divided by your actual is your relative error. And so that's less than 1%. That's less than 0.1%. That is 0.05 of a percent off. Okay. 1/20th of a percent off. So you say, yeah, it's acceptable. You move on to the next question. Now, how about, what does that do to measuring the length of the hypotenuse if you're off by 0.2 centimeters in each way, 0.002 meters? So the equation that relates to the hypotenuse, if you call the hypotenuse z, then it's the Pythagorean theorem. The fact that z is equal to the square root of x squared plus y squared. So then we take the derivatives, the partial derivatives. We do 1 over 2 square roots of x squared plus y squared, and then we multiply by 2x, and those 2's cancel. That gives us the x partial. There's the y partial. And so we are plugging in 5 and 12. It turns out that when x is 12 and y is 5, and you plug it into the formula, what comes out is that z is 13. It's one of our Pythagorean triples. So we have 12/13ths, and we have 5/13ths. But each one of those gets multiplied by 1 over 500. 500, that might be better. 2 over 1,000. So we have 10 over 13,000 and 24 over 13,000. Together they give you that. Now, what is that in relative sense? The z value is equal to 13. And relative to 13, this error here is less than 1%. It's less than 1/10 of a percent. Is 1/50th of a percent off. Okay, great. So big picture is that we can use the tangent plane to approximate our function. We can find out if we have small errors in x and y, how does that affect the change in our function? We've seen it back when we have tangent line. We say if I change x by a small amount, how does that change y? The actual change in y versus the differential change in y. So now what's going to happen in 3D? Well, the blue curve is going to come out of the screen and be a surface. The red line is going to come out of the screen and be a plane. And we have the blue surface and the yellow tangent plane. And we're going to then see then the comparison to the differential change in z versus delta z. Using the tangent plane as the approximator, we'll have a certain known value of a and b, or x naught and y naught, and we change x by a small amount, we change y by a small amount. The question then becomes, how does that change x and change y? How does that then lead to a change in z? And so this distance here will be the differential change in z, and this distance here will be the actual change in z. And the smaller that these delta x and delta y are, the smaller the difference is between the two. The more and more we move away, the more and more the approximation is off. And so that's it for tangent plane approximations. Hopefully this was useful. And now we'll move on from this tangent plane series. This is the last video of the 4. The links are down below for the other 3 if you want to go to them. Thank you for watching. Please like and subscribe and comment down below. Thank you.